Hello viewers, I am Kausalya. Today we are going to discuss about the topic state space representation using phase variables method 2. Here, consider the following nth order differential equation governing the output y of t to the input u of t of a system. So, here for the given differential equation, the input is u of t and the respective output is y of t. So, now consider this equation. So this is our differential equation, right? So here the dot represents the differentiated form. That is, y is in the differentiated form, right? So here this is our expression, right? Now here we are considering the value of n is equal to 3 and m is also equal to 3, right? And here this u of t corresponds to the input and here this y represents the output. So now since we had selected the value of n and m as 3, right? Here we are having y to the power n, right? So y is differentiated thrice, right? Therefore, we are having 3 dots here. And similarly, plus a1 into here y to the power, not to the power, here n minus 1. So 3 minus 1 is 2. So y is differentiated twice. So y, there are 2 dots above y, right? Likewise, here we are proceeding gradually. So here, what will be the next term? The next thing will be a2, right? Here a1, right? So the next step is a2 and y is differentiated once. And the next thing is a3 and the original form of y. Likewise, here also we are doing the same thing. Initially, the value of m is 3 here. So, therefore, the input u is differentiated thrice. And the next one is b1. The input is differentiated twice. And b2 input is differentiated once. And here the original form of input. Right. So, the next step is we are going to take the Laplace transformation. So, when you take Laplace transformation here, that is here the y is differentiated thrice, right? That is dy cube by dt cube. So when you take Laplace, we will be having expression as s cube y of s plus here a1 into s square into y of s and here a2 into y dot. Therefore, a2 into s into y of s and here a3 into y of s, right? And the next thing is again b naught into s cube into u of s plus b1 into s square into u of s and b2 s into u of s and b3 u of s, right? Just we are taking Laplace transformation, that's it. And the next step is here we are taking y of s term commonly outside. When you take y of s commonly outside, the remaining terms are arranged like this, right? Similarly, here we are taking u of s outside. So when you take u of s outside, these are the remaining terms here. And next, as we all know, the ratio should be in the form of output to input, right? So y of s is the output and u of s is the input. So y of s by u of s is of this form. And the next thing is here I am taking s cube outside both in the numerator as well as in the denominator. So when you take s cube here, that is what it means. We have to divide this numerator and denominator by s cube. That's it, right? So here b naught, s cube cancels each other. And here s square by s cube means, what does means? So these two cancel. So b1 by s is the remaining term. Likewise, b2s by s cube means b2 by s square. And here b3 by s cube, right? Likewise, in the denominator part, again when you take s cube outside, we will be having terms like this, right? So, both the numerator and denominator term cancels each other, and here we are simply rewriting the above expression. That is, you see, I am splitting this plus as minus into minus, right? So minus into minus will give you plus, right? So I am splitting this plus into two minus signs. So here I am writing it as 1 minus of, right? So minus of the entire term, right? When you move this minus inside, you will get this expression. You can check. That is minus into minus plus. Again this minus into minus plus, and minus into minus again gives you a plus here. right? So here we are going to use signal flow graph. So the Mason's gain formula, it is given by 1 by delta summation of k pk del k, right? So del is nothing but 1 minus sum of loop gain of all individual loops plus sum of gain product of all possible combination of two non-touching loops, and it goes on, right? And the next thing is pk. pk is nothing but path gain of the kth forward path, and del k is nothing but del for that part of the graph which is not touching the kth forward path, right? So these are all the things which we had already discussed, right? So just an introduction about this is Mason gain formula, that's it. So the next thing is, here when you look at the transfer function, you see this is our transfer function, right? This is the transfer function. So when you look at this transfer function, from the transfer function we can tell that how many forward path gains are there and how many feedback loops are there, right? So here the numerator terms contribute to the forward path and the denominator terms contribute the loop gain, right? So here how many terms are there? We are having 4 terms. So there are 4 forward paths. And how many individual terms in the denominator? There are 3 terms, therefore 3 feedback loops, right? So from the transfer function we are writing here, this is a transfer function with 4 forward paths and 3 feedback loops, right? So now we are going to compare this transfer function with the standard format. So just assume this is a standard format of the transfer function. And now when you compare these two transfer functions, you see here P1 is equal to B0 and P2 is equal to B1 by S. P3 is equal to B2 by S square and P4 is equal to B3 by S cube, right? Similarly, P11 is equal to minus A1 by S. P12 is minus A2 by S square and P13 is minus A3 by S cube, right? So these are all the things I had written here, right? Am I making things clear? Just from the obtained transfer function, we are comparing that transfer function with some standard format and we are writing down the expressions for the forward path gain as well as for the individual loop gain, right? Now we are going to draw the signal flow graph. So here just we are having 4 forward paths and 3 individual loop gains, right? So here this is our signal flow graph. So observe carefully, then only it will be easy for you to draw. So here we are having the value of n and m as 3, right? Right, that is the first step we had already seen. So when you have the value of n and m as 3, totally we will be having 6 state variables, that is differentiated form and the original form. You see here we are having x3, x2 and x1, right? And there will be differentiated form of those 3 state variables, that is x1 dot, x2 dot and x3 dot, right? So here we are starting with x3 dot. So now x3 and x2 dot x2 and x1 dot x1. So totally how many nodes are covered here? 1, 2, 3, 4, 5, 6. Okay, 6 nodes are covered for the state variables. Apart from these 6 nodes, we have to place 2 extra nodes on both the sides. Okay, one at each side. Here, this is another one extra node and this is another extra node. Apart from that, we should place nodes for input u of s and as well as for the output y of s, right? So here we are having 3 state variables. So the differentiated form of the state variables contribute for the next 3. So totally 6 nodes. So place 6 nodes first. After placing 6 nodes, we have to place another 2 nodes, one at each side. Okay, one at the left hand side and another at the right hand side. So these nodes are the respective extra nodes, right? Apart from this, there will be one node for input and another node for the output, right? So this is the first step. We have to know how many nodes are there in the signal flow graph, right? So Next thing is, as usual, you leave this is u of s and this is y of s, and these two nodes we should not mention anything, right? Just leave it. And here you start with x3 dot. Okay, when it is integrated, the integration is given as 1 by s, we will be getting x3, right? And the next thing is x2 dot, and when x2 dot is integrated, we will be getting x2, and x1 dot is integrated, we will be getting x1, right? Right? So whenever integration is done, here we will be having 1 by s. So first finish these things, right? So after finishing, the next thing is, we know the values of the forward paths, right? So the value of the first forward path is b naught, okay? So let me write here, p1 is equal to b naught here. So here it is 1, that is in the input this line contributes a gain of 1, and again this line also contributes 1. So the entire forward path gain is only b naught. So here we start here and it moved to this node, and here it directly goes to the final, that is this node, and ends with the output. So here the respective value is b naught. Okay, so this is your first forward path gain. And the next path gain value, that is, it is given as p2 is equal to b1 by s, right? So we need b1 into 1 by s, okay? That is the expectation. So here again we start from here and we move to this node, and here we are traveling over here, right? We need only 1 by s, right? So to this path it has a gain of b1, and here we are having 1 by s already, right? So to the output, when you calculate the forward path gain, you see this and over this. So b1 into 1 by s, so which is b1 by s, right? So this is our second path gain. And when you look at the third path gain, it is b2 by s square, right? So we need 2s. So here there is 1 by s and here there is 1 by s. Only when these two are multiplied, we will be having 1 by s square, right? So here the third path, we are again starting and we are moving to this node, and we are that is we are moving over this path and we are ending with this node. Okay, now when you calculate the forward path gain, you see 1 into b2 into 1 by s into 1 by s. So the total is b2 by s square. When you multiply, the final answer will be like this, right? And the final forward path gain is b3 by s cube, right? So here in this case, you see I'm having 1 by s into 1 by s into 1 by s. So the thing what I need is b3. So here I am having b3, and this is your fourth forward path, right? Only with the help of this forward path we are drawing this signal flow graph. Am I making things clear? The first step is you have to know how many nodes are there in a signal flow graph. That is your first thing. And the next thing is you have to place the state variables in the respective nodes, right? So once you place the state variables, then whenever there is an integration, you have to introduce 1 by s, or else just the gain and that part of the loop is 1. That's it. When you finish this one, drawing this forward paths are pretty easy, right? So now the forward path gain is calculated. Next we have to calculate the loop gain, right? So when you consider the first loop, you see the loop gain value is minus a1 by s, right? So here you see I'm having 1 by s here. So when I include minus a1 in this path, so the loop gain will be minus a1 by s, right? So here I had drawn a1. And the next thing is the second loop gain is minus a2 by s square. So as usual, 1 by s into 1 by s, this contributes s square. So you start a loop from here and just proceed over here and end over here. So here it is minus a2. So minus a2 into 1 by s into 1 by s gives minus a2 by s square, right? And the next thing is third loop gain is minus a3 by s cube, right? So here we need s cube, right? So you see 1 by s into 1 by s into 1 by s. So here again I am starting a loop over here, right? And here You see, in this part I'm having a gain of minus a3. So minus a3 into 1 by s into 1 by s into 1 by s gives minus a3 by s cube. Right. So finally we had drawn the signal flow graph. So drawing a signal flow graph is the most important part here. Right. I hope I had made the concept clear. So next we are going to write the expressions. So you see, I want expression for x1 dot, x2 dot and x3 dot. So here I need expressions for, first we are considering x1 dot. So first locate where is your x1 dot. So this is my x1 dot, right? So just draw the things from the signal flow graph here, that's it. Okay, so here I am having x1 dot, right? To this x1 dot, how many incoming signals are there? Here I am having one from this x2. So x2 here comes over here, so in this part the gain is 1. And next here I am having this b1, right? This b1 comes with this input part, so b1 into u. So here, so here I am drawing b1 into u, and here this part is x2, right? You see, here x2 and this is b1 into u. I had written those two things to the x1 dot, right? Then apart from that, I am having some other thing which are connected to x1 dot. So to this x1 dot, I am having a minus a1, right? And this minus a1 is coming from this node. So here that node is drawn and minus a1 is drawn here. And to this node again I am having two inputs, right? So here again one that is this node, right? So here from this x1 is moving over here, and again here b0 into u. So here x1 and here b0 into u, right? So just the first step is you have to draw this signal flow graph for the particular state variable. You should be very precise in that, right? So after drawing the diagram, the thing is just we have to add, that's it. So here you see this x1 dot is nothing but it is x2 plus b1u, right? So here you see x2 plus b1u, and here the thing is minus a1, and this minus a1 gets multiplied with these two inputs, right? You see, because to this node two inputs are there. So here x1 plus b0u is the output from this node, and this signal gets multiplied with this minus a1. So here minus a1 into x1 plus b0u, right? Am I making things clear? The first thing is, to this x1 dot I am having two inputs, okay? Just those two inputs are with positive sign, so simply add x2 plus b1u. And the next thing is, again to this node I am having some other thing which is connected. So when you look back, you see here I am having a node, and this node is also having two inputs. So what will be the output of that node? Both are with positive sign, right? So x1 plus b0u, and this x1 plus b0u gets multiplied by the gain over here. The gain in this path is minus a1. So when you multiply minus a1 into x1 plus b0u, right? So just the thing is, again you have to multiply this minus a1 with the things inside the bracket. After multiplying, just we are combining the similar terms, a1 x1 and here this x2, and these two terms both has u, right? So we are taking u commonly outside, that's it. So finally we had framed an expression for x1 dot. And similarly we have to sum up the incoming signals at x2 dot, right? Again move back, right? So here this is our x2 dot. So to this x2 dot, how many inputs are available here? Again one from x3 and another from b2 multiplied by u. So here x3 and the another input is b2u. And again when you look at this x2 dot, that is another signal which is coming, and here it is minus a2, and this minus a2 is fed with again some other inputs, right? This minus a2 is coming from this node, and this node is again fed with this x1 and this b0 into u again, right? You see, to this node one input is from this x1 part and another is from b naught, which is multiplied by with the input here. So just draw the diagram as usual, and again we have to write the expressions. So x2 dot is given by x3 plus b2u, right? x3 plus b2u, and here this minus a2 will get multiplied with summation of these two terms, that is x1 plus b naught into u, right? So that is the expression here. Again you have to multiply the terms and combine the similar terms together, right? And finally again we are going to do the same thing with x3 dot. So when you move back, you see this is our x3 dot, right? So to this x3 dot I am having one input over here, right? That is b3. This b3 is get multiplied by with this input, so b3u is one of the input here. And to this x3 dot I am having again minus a3, and to this node again the two inputs are the same, right? Here x1 and here plus b naught into u. So the same thing we are doing with x3 dot. Okay, we are writing expressions and finally we are combining the common terms together. So finally we had framed expressions for x1 dot, x2 dot as well as x3 dot. So now we are going to write the expression for output, right? So again when you look back at the signal flow graph, so this is our y of s, right? So here what will be the output here? Here the output is given by this x1 along with this b naught into u, right? So here we are writing the output expression as x1 plus b naught u, right? So now we are going to write in the matrix form, right? So first consider this state variables. Okay, when you write it in matrix form, x1 dot, x2 dot and x3 dot is equal to the respective coefficients. So here the coefficient of x1 is minus a1, x2 is 1, right? So similarly here there is no x3 coefficient, so it is 0. And again when you consider this second one, coefficient of x1 is minus a2 and x2 is 0 and x3 is 1. And here coefficient of x1 is minus a3, no x2, x3 both are 0, right? So here x1, x2 and x3 plus here we are having u, right? U is nothing but input matrix. So here the coefficient of u is b1 minus a1 b naught, and here b2 minus a2 b naught, and here b3 minus a3 b naught, which gets multiplied with the u matrix, right? And when you frame expressions for output, you see here we are having x1 as well as u term here. Therefore the output matrix is written as, here y is equal to x1, right? So the coefficient of x1 is 1, no x2, no x3, which gets multiplied with x1, x2 and x3 plus, and here we are having b naught u, right? So b naught into u finally, right? So we can again rewrite the above matrix in the generalized format for an nth order differential equation. So here when we write for nth order differential equation, you see here the expression will be like this: x1 dot, x2 dot, it extends up to x to the power n dot, right? And here again when you write the expressions, you see here we are having a1, a2, a3, right? And the general expression will also consist of the same, right? They are with minus signs, right? So minus a1, minus a2, minus an, and here the remaining terms, they remain the same, right? So similarly here x1, x2, xn, and the thing is xn minus 1 plus, again the same thing here, the final expression is in terms of n, that's it, right? Similarly the output also we will be having like this, right? So here comes the end of this derivation. Based upon this, we are going to solve problems also in the future. So if you have any doubt, let me know in the comment section. Thank you.